Hi, my name is John Krochmalny, and I've developed these visual tutorials to accompany any technical training format that might be delivered. Three-phase electric motors will be covered in this presentation. Explored will be where they are used, how they work, and how to do normal maintenance on them. There are three learning outcomes associated with this presentation. Number one, define induction. Number two, identify three-phase motor components. Number three, describe three-phase motor operation. And number four, describe three-phase motor measurements. Emil Lenz, back in the early 1800s, discovered that when current passes through a conductor, magnetic lines of flux are generated and surround the conductor. As with any magnet, there are north poles and south poles associated with these flux lines. The greater the amount of flux lines, the more powerful force of either attraction or repulsion results. Placing a magnet in the presence of another leads to either an attraction or repulsion. In this graphic, we see the similar poles of flux lines facing each other and therefore a repelling force. In the bottom bar magnet, we create a pivot that could cause rotation. Under this installation, we find that a rotational movement could happen as a result of the repelling force of the flux lines. This is the operational principle behind electric induction motors. The power of a motor is associated with the number of flux lines generated in the motor coils, resulting in an increase of the repelling forces. In single-phase induction motors, the current passes through the motor and only comes from one direction per unit of time. In this case, all of the current comes from the L1 terminal and travels to the N terminal. Since we have 120 volts AC as the power source, this voltage appears and disappears according to the frequency of the AC power source. It is this difference in voltage pressure that causes the current to move through the circuit. Electric induction motors convert electrical energy into rotational mechanical torque to perform the work. They are called induction motors because the flux lines generated in one coil results in a voltage induced in the other. If there's a difference in voltage in the induced coil, there will be a current flow in that induced coil, resulting in the generation of its own flux lines. All motors have similar components. When referring to induction motors, the major components are the stator, the rotor, the shaft, and the bearing. The stator of an induction motor is the coil that is stationary. This coil does not move, but receives the current from the motor's power source. As current passes through the stator coil, magnetic lines of flux are generated. The leaving side current of the stator coil has the north pole orientation of the flux lines. The entering side of the stator coil has the south. As you can see in this graphic, the stator coil is a wound copper coil conductor. This conductor is coated with an insulation that prevents short circuits happening when the conductors touch. The rotor is the motor part that rotates under the influence of the flux lines. In this simplified graphic on the left, we see the opposing flux lines causing rotation. In reality, the rotor is also a coil. When the stator flux lines appear and collapse across the rotor coil, voltage is induced into the rotor. Because this voltage has a difference in value from one side of the rotor coil to the other, a current is generated. When this current flow from the higher voltage source to a lower, it generates its own flux lines, which are in opposition to the stator flux lines. The rotation of the rotor results. Other key motor components include the shaft and bearings. The shaft is locked into position in the rotor and rotates with it. Because there could be friction among parts that move, bearings are installed. These shaft bearings are lubricated to reduce wear. In regards to three-phase motors, they all have three stator windings or coils, one rotor, considered another coil, and a three-phase power supply. This graphic represents the three-phase power supply wired in delta configuration and intending to be the supply power to a three-phase motor. Notice that the voltages measured phase to phase equals 480 volts AC. Phase-to-phase voltage measurements are measured from L1 to L2, L2 to L3, and L3 to L1. Delta-configured transformers used in industrial applications will measure 480 volts AC. This 480 volt AC is made available to the three-phase induction motor expecting this voltage. In this graphic, we see three winding coils wired into a delta configuration for this 480 volt AC supply. With a three-phase power supply, we can understand each phase having a voltage appearing on each phase, but not at the same time. Phase 1 grows to a maximum voltage before Phase 2. Phase 2 grows to a maximum voltage before Phase 3. In this graphic, we see Phase 1 at a maximum value compared to the other phases. This imbalance results in an amperage flow coming from L1, entering the termination, and then splitting two ways. One path goes to L3, and the other path goes to L2. As it does so, flux lines are generated around the two associated windings. Now in this graphic, we see Phase 2 voltage at a maximum compared to Phase 1 and Phase 3. This imbalance results in an amperage traveling from L2, approaching a termination and splitting in two. One amperage travels toward L1 and the other travels to L3. These two amperages are responsible for the generation of flux lines in the associated windings. Now we see that Phase 3 has a maximum voltage compared to Phase 1 and Phase 2, resulting in amperage originating at L3 and pushing toward L1 and L2. As the amperage passes through the coils, flux lines are generated in these windings. The flux lines generated in sequential order in the stator windings of a three-phase motor impacts on the rotor. This results in the rotation of the rotor. Because these types of motors are supplied with three-phase power supplies, maximum power is manifested by the three-phase motor. As mentioned earlier, industrial delta configured power supplies provide 480 volts AC to users. When Y-configured power supplies are used in industrial applications, 460 volts AC is delivered. Three-phase motor measurements will consist of voltage and amperage. Both types of measurements are done with power supplied to the motor. This graphic assumes an applied voltage measurement on a Y-configured three-phase motor. In this measurement, the voltage meter is placed across the phases to measure voltage phase to phase, L1 to L2, L2 to L3, and L3 to L1. The measured voltage is compared to the voltage identified on the motor nameplate. In this graphic, we see an amperage rating of a properly loaded motor. When under a load, this motor's amperage cannot exceed this value. Powering the motor under a load, we measure amperage by using a clamp-on ammeter to record the value. Once recorded, we can compare the actual condition to what it's supposed to be.